This is a little video about the chain rule. So this is where we are looking at a composite function where we have plugged the value of one function, say g of x, into another function that would be f of x. So far we have seen slightly different that there's different ways of combining functions. If we add them, we have f plus g, and then if we take the derivative of that, we just take the derivatives of the individual functions. So f plus g prime is f prime plus g prime. F minus g prime is f prime minus g prime. F times g prime, that's the product rule, would be f prime g plus f g prime. And then f divided by g prime is the quotient rule. That is something where you will have f prime g minus f g prime, and all of that is divided by the square of the function g of x. Now, when we have compositions, we are not adding, subtracting, multiplying, or dividing. We're actually plugging one function into another. So for instance, if we have y is equal to the quantity 2x plus 3 raised to the 52nd, well, then we have said that we take the function g of x, which is the 2x plus 3, the inside piece there, and we've plugged that into the function x to the 52nd. So we have g of x would be this piece here, is the small function that is on the inside, and it is plugged into the piece of the function where you're raising it to the 52nd. And we would expect the derivative to depend on both functions f and g. If we're both finding a linear equation, 2x plus 3, and then plugging that into the x to the 52nd, we would expect that both of those pieces actually tell us a little bit about how the function changes. So another example, if we had e raised to the 5x minus 7, then the inside function, the g of x, is the 5x minus 7 part, and that is plugged into the equation e to the x. So here we see this piece, the line 5x minus 7, is plugged into the function e to the x. And so again, we would then expect the change in y to depend both on the 5x minus 7 piece and the exponential part of the function. So the chain rule is where if we take f of g of x, we take the derivative, then it's equal to f prime of g of x, so the derivative of the outside function, just evaluated at the internal piece, times g prime of x. So in other words, we take the derivative of the outside function and we multiply it by the derivative of the inside function. So here we have a piece that is the derivative of the outside function, and it is multiplied times the derivative of the inside function. So you can think of this as being a product here. So for the example that we saw on the previous slide, if y is 2x plus 3 raised to the 52nd, then the inside function is your g of x, that is your 2x plus 3. The outside function is the x to the 52nd. Then if we take the derivative, we first take the outside function, the derivative. Well, that would be 52 times whatever the inside function was, and then raised to the 51st. Because we had the function where we're raising it to the 52nd, and if it was just an x on the inside, then the derivative would be 52 x to the 51. And it just happens to be that here, now it's just evaluated at the function g. And then we still have to make sure that we multiply it here by the derivative of the inside function. Now, it might be that at this point your head might start spinning because you have all of these inside and outside functions. So what people often do is help themselves a little bit by doing a substitution. So it kind of helps you write down your formulas and not get confused about where you're still taking derivatives and where you're just plugging in a function. So if we talked about f of t is this quadratic where we have the t squared plus 5t minus 7 all raised to the 101th power, then we think of this as the outside function, which is our f of u is equal to u to the 101. That is the big outside function. The inside one is the piece that is in the parentheses. So that's the t squared plus 5t minus 7. Then the derivative turns into the derivative of the outside function times the derivative of the inside function, which is just f prime of u times u prime. This is not saying anything different than what you saw on the previous slide, but it cleans it up a little bit. By substituting a u for your internal function, for your inside function, you now actually have a much cleaner notation. And so the derivative of f would be 101 u to the 100, because that's the derivative of your u to the 101 function, and then times the derivative of the inside piece. Well, if you're looking at your t squared plus 5t minus 7, you take a derivative of that, that is 2t plus 5. Now, in the final step, you have to make sure that everything is back in terms of x. In this case, actually, it's in terms of t, because your original function was written in terms of t. The only thing you need to do then is to take every u and replace it again by the original substitution. So every time you see a u here, it becomes a t squared plus 5t minus 7. And that's how you get this kind of long and complicated looking function, but that is the derivative of f. So let's look at a couple more examples. Here we would be looking at put a text box in. So we have a function here. If you're looking at the inside, it would be that if you started to plug in numbers, it's where you start to plug in numbers first. So if you had f of 1, you'd start to try to plug 1 in for the p to the 4th plus 3p plus 5. So that tells me that u is equal to my p to the 4th plus 3p minus 5. So that's my inside function. And that means that I now have f of u is equal to u raised to the 6th power. Because after I've replaced the inside piece, I just get a u raised to the 6th power left. Well, then my derivative, f prime of p, is equal to f prime of u times u prime. So I take the derivative of the of the second one, my f prime of u. So this is equal to 6 times u raised to the 5th. And then I'm going to multiply it by the derivative of the inside piece, which would be this one. So the derivative of that is equal to 4p raised to the 3rd power plus a 3. And I'm almost done because I now have an equation for the derivative, but notice that I have two different variables. I have a u sitting around here and a p. I want to always go back to my original variable because that's how I defined my problem. P is probably the price and u is just some function of that. So we want to go back to that original variable p. So this would be 6 times, I'm going to take u here, raise it to the 5th power, and then multiply it by that last piece. There we go. So that's how you find the derivative. You basically do the initial step where you're doing the substitution. You find out what the substitution u is. You write down what the outside function is in terms of u, and now you just string the derivatives together, and that will always work. So for instance, for this one, if we were to kind of look at this equation, then the inside function would be the u is equal to my q squared minus 12. That is the inside piece here. And then what I would have left is my g of u is equal to the square root of u, which we probably should write as u raised to the 0.5, because it's easier to take a derivative of that way. So now we would find that g prime of q is equal to g prime of u times u prime, and that in this case is equal to my g prime of u is going to be 0.5 times u raised to the minus 0.5, because that's how I take a derivative of this function here of my u raised to the 0.5. This is just a power function. The 0.5 comes out front, and then you get u, and then it's raised to the 0.5 minus 1, which gives you minus 0.5. Now I still have to take this and multiply that by the derivative of u, which, and always put that in parentheses, is going to be 2q. In this case it's kind of clean, but it's always better to kind of be safe and put the derivative of u in a parentheses, because it's possible that it's a longer, more complicated equation. And just like before, we're almost home free now. We would have our function almost done, but we have to put everything back into the original variable. So we're going to put everything back in terms of q. So it's going to be 0.5 times my q squared minus 12 raised to the negative 0.5, and then we multiply by 2q. And that's how it works. The software I have doesn't really allow me to write that a little cleaner, but I think with the q caret 2 you can kind of see what the pattern is here.